Okay, so I welcome you folks, for those that are here, for those that are here at a distance. For those that are here at a distance, I'm sorry I can't offer you the granola bars that are here, but those folks that are present in this room, there's some granola bars. But I also want to point out that I have these little baggies, and in these baggies are these little model kits, and I have 8 of them here. And I can make more. So I'm just going to leave them on the chair. They don't look like much, that they're just these little green straw-like things, and a couple of pieces that are in the shape of tetrahedrals and bent shapes and stuff. But if you're having trouble visualizing chairs or conformers and chains, actually, this is all you really need. So you're welcome to take this, and I don't need them back. You can keep them. And that's in part why I'm putting these out, because in the past it was sometimes hard to get things back. And I would worry more about the proper model kits, but for these, you're more than welcome to keep them if you wish them. So I'm just going to put them over here. You can use them in a test situation, exam situation, and if we need more, I can make more. Okay, so today, finishing off Chem Activity 6. Next week, next Thursday, of course, we have our term test, which is, yes, on a lab day. I will find a better room rather than the lab. Okay, so I keep posted on that. Our next class is actually next Wednesday. And yes, during this section, we've got mass spec, we have IR, we have NMR. And yes, there are videos in each of these, for each of these sections. So there's Chem Activity 7 parts 1 and 2 videos for next Wednesday. It just allows us to be able to spend a little bit more time doing practice and delving a little deeper. And so I do ask you to engage with those. Of course, if you don't have time to watch before class, please be sure to watch after. And I try to kind of give the context during the lesson. Where I'd like to pick up is on page 46. And this is, in a sense, we left off with this analysis of the mass spectrum. Oh, why didn't you say anything? For the folks that are at home, I'm talking away. I'm looking at the screen. It's all looking good to me. But of course, the students here don't see anything because I didn't turn on the projector. So, and in fact, I didn't even plug in the projector. So, okay.
Okay, so it's not completely our fault.
Well, yeah, no, it is all my fault. It's, I, for some reason, thought I had more time this morning. Screen sharing has stopped because of an external display. So that's all good. I'll just do that again. Okay, so. There we are. Hey, we're all back. Okay. And so I'm just going to move these folks over to the side here. Not there. Okay. Oh, come on. There we are. Beauty. That's not what I want. Okay. So as I say, we're on page 46. We just finished doing last time this analysis where we were making use of a couple of things to come up with the formula. So I just want to remind you that we've identified this idea of the parent ion or the molecular ion. And of course, it gives us the mass. It also gives us some additional information. Recall that if it's an even number, then chances are there are no nitrogens in the compound unless there are 2 nitrogens, for instance, or 4 nitrogens. If it's an odd number, then definitely there's a nitrogen in the compound. Then we started to look at the M+1 peak, and we saw that it gives us a sense of the number of carbons. And you can do a fairly simple calculation based on the fact that 1.1% of the carbons are C13. More recently, we saw that we may even want to pay attention to the M+2 peaks. And the patterns are that if you have an M plus and an M plus 2 that are of about equal abundance, well, then there's a good chance that you have a bromine. If you have an M plus and an M plus 2 where the M plus 2 is 1/3, good chance that you have a chlorine. And so we took advantage of that with this particular spectrum. You will see, for instance, in some of the questions in Open OChem, when you start to take a look at it, that I might, some of the ways I've asked the questions is to give you a series of mass specs and then a series of compounds against which to identify. And those are the little things that you're looking for. So you'll see, for instance, there'll be 4 compounds listed. 2 of them have halogens, one bromine, one chlorine. So you're looking at around the area of the mass spec for, those telltale signs. One of them is going to have nitrogen. So you're looking for an odd number around the molecular ion peak. So that sort of thing. So we came up ultimately with this formula, and that's essentially where we ended. But there was an additional question, and it said, show the fragmentation pattern that would produce the base peak. So recall the base peak is the peak that is in the greatest abundance. And sometimes you're able to explain, where that peak comes from because there's an obvious fragmentation pattern. And in this particular case, there is pretty much an obvious fragmentation pattern. And I write the reaction down here, but I haven't really explained it at all. And I think what I'd like to do is kind of show you from scratch. So I'm going to move the slide forward to one where there's less stuff written. And I'm hoping that you still have some space on page 46. And, I'm just pointing out to you that, yeah, we've already come up with the formula. So here's the formula, the general formula. And what I want to do is explain this base peak. And it is helpful to keep in mind what the corresponding numbers are in terms of the masses. And so the mass here is 90 atomic mass units. And the base peak is occurring at around 55 at 55 atomic mass units. So the difference between those two numbers should be pretty obvious. It's 35 atomic mass units. And so that's what gets lost. And of course, that's the mass of the chlorine isotope, 35 in terms of nominal units. So if I ask you to show the fragmentation pattern, it would go something like this. And I'm starting with this example, but throughout this lesson, we're going to be talking about doing the fragmentation pattern. And the idea here is you need to start with the radical cation. And this is something that seems to be forgotten, or I somehow am not able to help students connect that when I'm asking for a fragmentation pattern, you're starting with the particle that is your molecular ion. So not the formula of the compound, but it would look something like this. And let's see, yeah, I'll do it this way. So I'm going to go C4, H7, Cl, and I really should specify which particular isotope. So I'm going to go 35. I put this whole thing in brackets, plus, and then dot. That's what you're starting with. Not just the formula, but, the fact that you've got this radical cation. That's what that is. You can't detect it unless it has a positive charge. Because I'm kind of running out of room to go horizontal, I'm going to go down vertically. And so what happens is, of course, that fragments. And what does it fragment into? Well, we lose the chlorine 35, but the chlorine 35 is not detected. And so how we lose it is as the radical. It's the neutral particle. Of course, there are other pairs of electrons in there, but there is a single electron. And that's what we mean by the radical. And what we're actually detecting is this C4H7, which we can put brackets around and a plus like that. And so those two things is what results due to the fragmentation. And if you want to verify, we can do a quick little calculation here. So 4 times 12 for the 4 carbons that are there, 48, plus 7 times 1, again, nominal masses for the hydrogen. Well, that comes to 55 atomic mass units. So this thing that I've written right here is the fragmentation pattern that would explain the parent ion down to that base peak. Of course, you could do the same thing for chlorine 37, except what you'd be starting with then would be the M+2 peak. And so actually, just for completeness, so we drew one fragmentation pattern. We could also do the following, and I think I can squeeze it in here. So I could go C4H7, chlorine 37, in a corresponding way, that would fragment. This time, though, it's chlorine 37 dot plus, and then the C4H7. And so that fragmentation pattern would then explain going from the 92 down to the 55. Both of those things are happening. This one, in a sense, would be occurring more often because there's more chlorine 35 compared to chlorine 37. Questions about that? All right, okay, all right, good. Because as I say, this is in addition to doing the interpretations that we've done so far, these are some of the things that I ask you to do. And I'm, from my experience, somehow I haven't able to pass the message along well enough that students do it with facility. So that's why I'm trying to emphasize. And today we'll be doing that as well. Okay, so just wanted to double check something. Oh, yeah, we're all good. Okay, so then, before we move on to look at the things that were discussed in the Chem Activity 6 videos, parts 5 and 6, we're kind of go backwards for a minute. I want to fill in a little detail. So I'm going on to page 47. So I'm going forward in the course pack, but backwards in terms of concept. Because so far I've been talking about this formation of the molecular ion, and maybe just to come back here, you know, we've been talking about these molecular ions, radical cations, and essentially we draw brackets around a molecular formula and put plus and a dot, and I'm saying, you know, we don't really know exactly which bond has had an electron knocked out. We don't really have to know. So we write this in a general way. And that's certainly true for if you're dealing with an alkane, it's a pure hydrocarbon. But when you're dealing with certain functional groups, and especially those that contain oxygen and nitrogen, there is a more common molecular ion that's likely to form than others. So here on page 47, this is what I want to highlight. And so I describe all of this in a paragraph. At the bottom is the situation of the alkane, or an alkene would also be true, you know, essentially a hydrocarbon. We bombard this with electron gun, electron is lost, we have a radical cation. Where exactly is the radical, the single electron? It could be in multiple places. So we draw a bracket and we show this. However, for functional groups like ketones, carboxylic acids, amides, amines, alcohols, ethers, the most likely electron to be knocked out will be one of the electrons associated with that heteroatom. And so often or at times, you'll be asked to predict what exactly does the molecular ion look like. And so you can see, I'm starting from this ketone, and we knocked out that electron, and we ended up with this radical cation. And in terms of the amine, well, we knocked out that electron. And so this is somewhat predictable. It's the most likely molecular ion, the alcohol, and then we ended up with this radical cation. You'll see that there will be questions like this in the open OChem. And again, for some reason, I'm having trouble getting this to land, because many times students will then ask me after, how do I know? And yes, you don't know typically for an alkane. But with these other functional groups, it's a matter of taking off one of the electrons from one of the lone pairs and putting a positive charge, okay? So as a little bit of practice towards that end, and I just want to back up. It may feel like we're kind of like the detour going back to molecular ion, but you'll see we'll make use of this in a couple of minutes. So here you have two examples, one an alcohol, one an aldehyde, and I'm asking you to draw the molecular ion that's likely to form from these molecules. And so, I've got room downwards, and I think you do too. So what would the molecular ion look like? And if this seems really easy, I hope it is, like it's meant to be. So what would the molecular ion look like? It's pretty predictable. Oh, so I hope, for instance, for the alcohol, you drew in 3 electrons and you put a positive charge. And again, when you get to those questions in open OChem, and I think actually in those cases, while in many cases when you're drawing structures, you don't need to put in the lone pairs, I'm pretty sure I set it up that you actually have to put in one of the lone pairs. You can also put in a single electron and put the positive charge. And here, dot. And in many cases, unless I explicitly say, draw the Lewis structure or draw a bond line and put Lewis dots, you often don't need to put lone pairs of electrons. They're implied. However, if you're asked about fragmentations, you're asked about molecular ions and things, it's really important that you put the radical electron, that you're indicating, we got this radical. So in a sense, the other lone pair here is somewhat optional. I'm including it just because, kind of fits, but the radical electron is not optional. Okay, so if you got that, awesome. So I'm now on page 48. This was discussed in some detail in the Chem Activity 6 Part 5 video. I'll just briefly review because I want you to do some practice with this. So in addition to looking at the molecular ion and interpreting things that are going on in relation to the molecular ion, we also would like you to do a little bit of interpretation related to fragmentation. And as mentioned in the video, sometimes students get kind of stuck. They want to interpret everything. And I am here to tell you, do not try to interpret everything. You're trying to take out the major ideas. And in this one little slide here, this one example of the fragmentation of pentane, this is some of the main ideas. That typically what happens is we lose fragments that are odd numbered in mass. We lose things like a CH3, atomic mass units 15. We lose things like a CH3CH2, atomic mass of 29. We lose things like 43 and 57 fragments. And often what we do is instead of actually labeling in terms of those fragments, the actual mass that the fragment has, we label them in terms of what got lost. Because that's kind of like more interesting. That M minus 15, that means a CH3 got lost. That means M minus 29 means a CH3, CH2, and I illustrate each of these. The other thing is well, couple other things. Note that we start from the radical cation. I don't like how I wrote that, so let me do that again. We start from the radical cation. Again, I'm sorry about keep harping on this, but I ask students in assignments or tests, and I say, do the fragmentation pattern, and students will write the molecule. No, you have to start with the radical cation. And then what results, though, from this kind of fragmentation, remember, what we detect are the positively charged particles. And essentially, the radicals get lost, and we see the cation. So it's always, not always, for alkanes, it's typically this pattern that you start from the radical cation, and then you end up with the cation and the radical. So you should anticipate writing both of those. And in this case, you'll notice that I'm being a little more particular about where the positive charge is. That's because, in a sense, we differentiate. We say, okay, initially, we don't know exactly which bond has the single electron, but when we draw this, we're saying, oh, yeah, it was probably this guy, or in this case, that would explain the fragmentation. This had the single electron, that would result in a positive charge here and the radical there. Or if the electron was here, the single electron, well, then we'd have a cation there in the end, and the radical would be here. A small little comment about when we say radical would be there. So I'm just going to highlight this guy. C, H, H, CH3. This is a neutral particle. And you may remember we said, okay, when carbon's making 3 sigma bonds, it will be charged. It will either be positively charged or negatively charged. Except in this case, it's carbon making 3 sigma bonds plus that extra electron. If you count the number of electrons that carbon owns compared to how many it normally has, normally 4, in this case, it owns half of those bonding pairs plus that guy. So it owns 4. It is neutral. Okay, so that's the thing about that radical. Now, I also mentioned in the video that in this case, it's hard to know why the M-29 is the base peak. And I certainly wouldn't ask you to explain that. So quickly going over this, again, if you haven't watched the video, I ask you to watch because I go into more detail, but I wanted to highlight those ideas. Sometimes when you're dealing with certain structures, such as the one that's found on the next page, so this is on page 49, and in this case, we're looking at the 2,2-dimethyl pentane, and we have this pretty large base peak compared to the other peaks, and that's happening at M-43. And in this case, I think we can justify why that might be the base peak. And hopefully it's fairly obvious to you that what's going on here is that to explain the base peak, we're assuming that it would be the bond that's between this carbon right here and that CH2 group, and that's the one that has the single electron. It's this bond that in a sense gets broken. We end up with this radical, and we end up with this cation. Of course, the cation is the thing that's detected. And that happens more often than anything else. And that's often related to the stability of these things. And so then in the video, I go in to remind us about the relative stabilities of carbocations. And so I listed here on this slide right there. And so again, if you haven't watched the video, I do encourage you to. We will be spending a lot of time coming back and looking at stability of carbocations. But the main message, because I know you saw this in first year, the main message is that tertiary is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl carbocation. I mentioned in the video that in first year, there was talk about stabilization by induction, pulling of electron density from the outside carbons into that central carbon. And I also mentioned it has to do with hyperconjugation, which is a concept I don't think Rick would have talked about, and I know I didn't talk about in first term or first year, but I'll be talking about it a lot in a couple of weeks. But the main message is the more carbons around that positive charge, the more stable it is. So here we end up with this beautiful tertiary carbocation, and it results in a peak that's larger than other peaks. I'm going to stop here for a second. Questions about that idea? Okay. And we'll be doing some practice on this. So I have a quick question for you. It's right here. And set the stage, or is it? My pages are sticking together this morning. Okay. So this is check your understanding number 8. So I'm just going to open it up here. If you've got your devices, it's a multiple choice question. So again, this is found on page 53, question 8. Which of the following reasons explain why some peaks are larger than others in a mass spectrum? And it's really just a reiteration of what we were talking about a second ago. Okay. There was a bunch of answers that were coming up, and now the correct answer is being honed in. So that's kind of nice. One of the statements is completely ridiculous. As we're voting in, which statement is completely ridiculous? Or well, maybe not quite so ridiculous, because I was missing this word just for a minute ago. So I was ignoring that was there, and I was like, radicals tend to give larger peaks than cations, and that would have been ridiculous because of course radicals can't give any peaks. But radical cations tend to give larger peaks than cations. Remember, radical cation would generally be the molecular ion, and often the molecular ion is not the major peak. So it's not as ridiculous, but it's certainly not a valid statement. Cations tend to give larger peaks than radical cations. Well, that's a true statement, but it doesn't really explain so much why some peaks are larger than others in terms of the more common thing. And so most of you have honed in that the larger peaks generally represent peaks that are more stable. Okay, so that tends to be the main pattern, the main thing to look at. B is definitely, maybe if there's going to be a ridiculous statement, it would be B that's ridiculous. C, that's actually fairly valid statement, but I think A is probably the best one here. And I think I've convinced a lot of you of that. So I know I went through those first two examples pretty quickly because they are discussed in the video. So here I want to slow down a bit and have you do some practice. And so I'm going backwards in the course pack. This is typically how things are asked about in assignments and in test situations and in OpenOChem, beyond identifying the molecular formula by looking at the molecular ion, the M+1, the M+2. We ask about show fragmentation patterns. So I'm looking on page 50. This is exercise 4. And I say, show the fragmentation pattern that would produce the base peak. And the molecule in question is this 2,3-dimethylbutane. Now, again, I'm not expecting you to name compounds, but I'm hoping that at least some of the naming you saw from first year has stuck. But if you ever do get stuck, and you're by yourself, well, you can always Google it. But if you're in a test situation, you can ask me. So 2,3-dimethylbutane would look like this. So you're starting with that as a molecule, but I'm asking for the fragmentation pattern. So take a minute, think about what could have happened to produce that M-43. And not only figure out what happened, write out the fragmentation reaction, if you will. So when we say show fragmentation pattern, it's like what I showed you right at the very beginning of class. You start with the radical cation. You may notice that the M+1 peak is actually quite tiny. And, if it wasn't labeled, you might have even had a hard time picking it out. Now, its mass there may not be entirely obvious. That's starting at 86. So the mass down here is 86 atomic mass units. And so in this case, it's actually quite true that the radical cation's size, abundance, is quite a bit less than the other cation. So I'm hoping that based on what I was harping on a little earlier, you would have started with something like this. Right? So you draw the structure of the full molecule, but then you put it in brackets and you put a plus and you put a dot, because that's the thing that's being detected right here. And look, there is actually a C13 peak. It's there. This tiny little thing here, but I'm not asking you to do anything with it. I already tell you what the compound is. And then we draw an arrow and we want to explain, well, how could this happen? And when I look at the molecule itself, I think, well, where is it likely to break to produce the more common fragment? Suggestions? Right down the middle. Yeah, exactly. All right, so I'm hoping this one's actually pretty obvious. What's likely is it's going to break right down the middle there. Now, it will break here and here and here and here. And actually, I can see where that peak would have been if it had broken at any of these spots. What sort of fragment would you lose? It broke here or here or here or here?
A methyl.
Good, a methyl. And so 86 minus 15, right, will give rise to this 71. So that's an M minus 15. Yeah. So we would be able to explain that, but clearly it's not the more abundant one. It's not the thing that happens most often. And if we look at the result of breaking that molecule right down the middle, we see we end up with this and with this. But we still need to do further labeling. One of these will be a radical, one of these will be a cation. The cation is sitting, and I arbitrarily chose the left-hand structure because the two structures are identical, and I put the radical on the other side. And in this case, it's kind of like there's some symmetry in that the atomic mass unit for this particle is 43. And if you're not convinced, I can write CH3, CH, CH3. So that's writing it as a condensed structure. And so I've got 3 carbons. So 3 times 12 would equal 36. I have 7 hydrogens. 7 times 1 will be 7. Add those up. 43 atomic mass units. So that's what gets lost. What gets detected is the carbocation. By the way, is this a primary, secondary, or tertiary carbocation?
Secondary.
Yeah, secondary. So remember, the way we know is, so you're dealing with this, and then how many other carbons are attached, right? So the second, which is relatively stable, right? So this is a secondary carbocation. So that would, in a sense, justify that forming, if you will. Not only is this a secondary carbocation, it's a secondary radical as well. So that's all you need to write. But again, I found that sometimes it confuses students a bit. So I just wanted for you to see that process. So this would be the fragmentation pattern. And we're often going to deal with minus 15, minus 29, minus 43, and so on. Questions about that? Okay, looking good so far. Well, how about this then? This is at the bottom of page 50. You can see we have a really tiny molecular ion peak. And then we have 2, it's hard to say which one's the base peak because it looks like they're approximately the same height. But we have 2 major peaks, one at minus 43, one at minus 57. This is 2, and this comes from the molecule 2,3-dimethylpentane. So 1, 2, 3, 4, 5, methyl group here, methyl group there. And in this case, I'd like you to write 2 fragmentation patterns that would explain both of those cations. What's going on? How does this happen? Note again that what gets lost is an odd number fragment. So pretend this is a test question and that I'm asking you to use the proper convention to show the fragmentation pattern. Minus 15 would be a methyl group, 1 carbon, minus 29, ethyl group, 2 carbons, minus 43. Yeah, that's a 3 carbon thingy. minus 57. Again, I hope that you're starting off with your radical cation. And in this case, we can start off with the same radical cation and maybe have arrows going in two different directions. And just kind of for the record, we do have an m minus 15 here. So we're starting at 100 and down to 85. So that would be losing a methyl group here, let's say, or a methyl group there. But we want to explain the m minus 43 or the m minus 57. And actually, it would be breaking the same bond to explain both of those. Which bond?
The one that's holding the two together.
Okay,
Or
yeah, right
that
there,
doesn't
right?
help.
You mean right
Yeah,
there.
that
Yeah,
one.
yeah, exactly. Yeah. And while it's not, I guess, entirely necessary, it's not a bad idea to do something like that. Well, I meant to change my pen color. You know, just for your own record or to kind of communicate to me that you're saying that bond will get broken. And what can happen is, oh, pardon me. What can happen is we can end up with cation right here and a radical there, or we can end up with a radical here and the cation here. Now, maybe we should do some labeling. Which of these resulting patterns, which one is the m minus 57? Exactly, the one on the left, right? So this peak here would be the m minus 57 peak. You know, the one that's occurring at 43. So essentially, it's 43 atomic mass units, but we're referring to it as the m minus 57 in reference to what got lost. Over here, this would be the m minus 43 peak in reference to what got lost. But of course, it would be occurring at 57 atomic mass units. So I'm hoping this is seeming pretty straightforward. Note that I'm not trying to explain most of the things that are going on. We could probably talk about this guy though. What would that peak there? How would you refer to it? What got lost from 100? Talking about this one right here. Good, 29 got lost, right? That would be the m minus 29. And how would we explain that? An ethyl group gets lost, right? So again, it's not everything. It's these common patterns. And sometimes you're going to see even just being able to recognize that will allow you to be able to distinguish between different molecules. Because in some molecules, there will be no ethyl that could get lost. In this case, yeah, a methyl, an ethyl, a propyl, and a butyl all can get lost. Okay, you seem to be on the right track. This is awesome from my perspective. So, two more examples of this kind of fragmentation. But now we're going to tie into something that I mentioned as a detour a couple of minutes ago. And this is something that where we're looking at fragmentation, not just from alkanes or alkenes, but from when we include heteroatoms, in other words, those more common functional groups. And here it's helpful to remember that the common molecular ion, when you have these heteroatoms of oxygen and nitrogen, the common molecular ion will be in or around that functional group, where one electron gets knocked out from the lone pair of electrons. So I'm going to do the first example with you. It's saying, explain the formation of the base peak from the molecular ion from a molecule of ethanol, and in a sense, draw the fragmentation pattern. So you're drawing that reaction. So let's start directly with our ethanol molecule. And note that if I just give you the spectrum, there's a little bit of ambiguity. If I don't tell you what this is, there's some ambiguity about where the molecular ion is. Because you might be saying, oh, here's the molecular ion, and you might say, that's the M+1 or something, right? It kind of looks like that. Although that's, or you might be saying, oh, maybe it's got chlorine in it. Although I hope you appreciate that it's really unlikely that it's an organic molecule with chlorine, because the mass isn't really high enough. Like chlorine would be taking up 35 atomic mass units, and then you only have 10, and carbon is already 12, so it's not likely chlorine. This is pretty high for an M+1 peak when it's only at 45, right? So there's a couple of reasons to suggest that that's not an M and an M+1, but there's some ambiguity. But I tell you what this molecule is, and so I hope you see or recognize that right here would be the molecular ion. And yeah, there's a big peak at 45. Well, it's probably a loss of a proton, but I'm not asking you to explain that. I'm asking you to explain the M, and in this case, it's at 31. So 31 atomic mass units. And this is equal to 46. So what kind of thing got lost? 46 down to 31. What particle got lost? This would be an M minus. Yeah, M minus 15. Okay, good. So you're trying to explain that, M minus 15. And when you look at this really simple alcohol molecule, it's not hard to imagine a methyl group getting lost, but a little bit more explanation. So we'll do this, and minimally, this is what I'd hope you would do. This would be, the simplest approach, and I would be happy if you did this. So I'm going to at first pretend that I don't really know where the dot is, if you will, in the positive charge. I'm just saying generically, because that's what we've been doing so far for doing these fragmentation patterns. And as Beth commented, well, of course, yeah, we're losing a methyl group. And the only methyl group that's in this molecule would be losing this, right? And so let's draw the outcome. Again, convention, the convention's important. So you're going to have a CH3 dot. So you're not seeing the CH3 in the spectrum, you're seeing the fact that it gets lost. But here we need to be a little more careful. So I go O, H. And where's that positive charge then? Actually, you're right, but it wouldn't be obvious, or it would be the one that would contribute the most. But just based on that it's this bond that gets broken right here, And based on the previous examples, so it's that carbon that has the radical. So where would we predict the positive charge, at least at first blush? Probably on the carbon, yeah. All right, so I would probably do something like that. All right, but Beth, ultimately, I like your answer, but we'll see why that's the case in a minute. Okay, so we'll do this, and this would be perfectly good. Now, no, it's not such a pretty carbocation, though. And it's not just because of my bad drawing. Because technically, it's like a primary carbocation. It's not very stable so far based on what you guys have seen. So minimally, I would hope you do something like this, and you would get full points. But I want to show you a little bit further background. And if you wanted to answer as I'm about to show you, that would be really great too. So let's this time start from a more sophisticated version of the radical cation based on what you know happens with heteroatoms. So instead of just doing this more generic thing, where would we expect the radical to be in the positive charge? So the electron gun shoots this molecule, knocks out an electron. What electron gets knocked out? What electron is most likely to get knocked out? On the oxygen, right? So we would do something like this, right? And we put the positive charge there. So more generic way, it's okay, but this I think is even better in the sense that, yeah, we know that that's what is likely to happen. Now, I realize that we haven't studied reaction mechanism in this course yet. And what I'm about to show you is even more bizarre. So when we studied reaction mechanism in first term, we would do something like what I'm showing in the upper left-hand corner to show, in a sense, the flow, electron flow of a pair of electrons. There's also a convention to show the flow of a single electron. It's a single barbed arrow. So here's what we picture is happening, and this is what's referred to as an alpha cleavage, where the carbon right next to the heteroatom is considered to be the alpha carbon. So you got alpha, beta in terms of this terminology here. And yes, it still will be this bond that gets broken, but what's imagined to happen is the following. You have here a single electron and a single electron coming to form a new bond, a pi bond between that carbon and oxygen. And a single electron comes onto the beta carbon, and that explains the radical. So those are meant to be single barbed arrows. The end result here is effectively the same thing. So we end up with this CH3 radical, and we end up with double bond, oxygen plus, and just for the record, that's a CH like this. And so this is why this is called an alpha cleavage. It's cleaving the bond between the labeling of alpha beta carbons there. So clearly this and this is the same thing. What about these two? Are they different molecules? Do you remember what that arrow means? Resonance. They're resonance forms. They're resonance forms. So I'm totally happy if you just want to draw this the more generic way. But then this actually gives a little bit more information. And I you know, I'm reluctant to promote this too much because we haven't covered reaction mechanism yet. Which resonance form would contribute the most? And I realized it was like our very first lesson, or maybe the second lesson, and we had a list of, you know, what results in a relatively highly contributing Lewis structure. And there's one really, really important, like the most important thing in terms of contributing Lewis structure. The octet rule. Yeah, and it's like, and I can't even justify the octet rule, but the more atoms that have an octet, the more likely it's going to contribute. And even though this is a positive charge on an oxygen, even though oxygen is pretty electronegative, this is the more contributing resonance form. So you could even go here, here, and then down here kind of thing. But I'd accept either one at this stage, okay? Because it's the same molecule, right? And it justifies that fragmentation pattern. Right? So these are a little more tricky, but I'm hoping you're seeing, not much. So let's try one more then. So now we have this molecule that you know about, you've seen before. This is acetone. And I'm going to label, you got alpha, beta. So the alpha carbon in this context is the carbon that's right next to the heteroatom. And I'm asking you to draw the fragmentation pattern that would explain the molecular ion. And to set the context, we have 57 atomic mass units, and we have 43 atomic mass units. So if you're starting to realize that methyl groups get lost frequently, right, then that's a good thing. Now, hold on. 43, 57. No, I lied. I can't count, or I can't read. There. That's better. So I hope you appreciate that right here is an n minus 15. Please show me the fragmentation pattern. You can go for the more generic, or if you're feeling kind of adventurous, you can go for the one that you're more explicitly showing the alpha cleavage. In case you're wondering, this is number 11, the bottom, page 51. So there's a very straightforward way, which would be totally fine on an assignment or test, or you can try to be a little more adventurous. And maybe even with these few examples, you could start to see that, whoa, this could get real complex. This could get pretty bizarre in terms of the various kinds of fragmentation, especially when you have to still deal with the single barbed arrow and think about these radicals and stuff. So I'm hoping at the simplest level, you just start with that molecular ion. You're losing a methyl group that could be on either side. CH3 radical. And in this context, where would the positive charge be? On the carbon carbonyl? Yeah. Okay. Yeah. Right here. And now, and of course, if we label these, this is 15 atomic mass units. And what's left over would be 43 atomic mass units. If you're not convinced, that's a CH3 C double bond O. If I count, I've got 24 atomic mass units from the carbon. I've got +3 from the hydrogen, +16 from the oxygen. So add all of those up, and that equals 43 atomic mass units. So that would explain those two fragments, or those two particles with the cation. If you want it to be a little more adventurous, so for the record, I'll do this as well. So if we start from acetone and lone pair dot positive charge on that oxygen, in this context, this is considered the alpha carbon beta. And what we'd expect is because we're anticipating that it's going to be, pardon me, the bond between the alpha and the beta that's getting broken. And let me just move my positive charge so it doesn't get in the way of the arrow. So we would have a single barbed arrow, if you will, coming there, single barbed arrow there, and single barbed arrow like that. And you might be a little bit surprised by the outcome. And again, you say, oh, we're making something completely different, but we're not really. And where's the positive charge in this kind of fragmentation? On the oxygen again, right? And what's the relationship between these two things? Resonance. And which one would contribute more? Again, because the oxygen has an octet. Yeah. So either way would be fine. Right? I didn't want to get it to be too complicated, but I felt like you guys had enough background that I could show you either way. And it just helps you, in a sense, the reason why this is helpful is it helps explain that, this is a fairly common fragmentation pattern, and we call this the alpha cleavage. And it's essentially breaking the carbon-carbon bond that's right next to where the heteroatom is. Okay, so folks, we've got about 15 minutes, which is just enough time to introduce one last set of fragmentations. So the more common one are these fragmentations where you're starting from the radical cation and you end up with a radical and a cation. But there are two other patterns I'd like you to be aware of. As I say, you could do a whole course on mass spec. So we'd be looking at hundreds of different patterns. No, essentially three major kinds. This, the radical and a cation, and then I got two others. So I'm looking at fragmentation of alcohols, and I realized just a minute ago I was saying, well, heteroatoms and the alpha cleavage. But what I'm about to show you is somewhat unique to alcohols. And in this case, I'm not so interested in you knowing about how it happens, but to recognize the pattern. And so I start with the radical cation on the left, and you can see I'm just using R groups to represent the alcohol. So those R groups could be hydrogens, they could be carbons. And I'm saying that what can happen is the OH from the alcohol can combine with a hydrogen that's on an adjacent carbon to result in an M-18. And M-18 fragment that's detected by the mass spec. Now, this kind of fragmentation has a fairly dramatic different outcome. One, yeah, we lose a water molecule, but there are two other things that are really worth noticing about how this is different. I'm going to ask you to take a look at it and just say, okay, how does this differ from what we just saw with the alkanes or the heteroatoms that fragment via the alpha cleavage? There's something that's going to look really different on the mass spec. Awesome. Yes. All right. You started with a radical cation, you ended up with a radical cation. Right. So that's different in its own right. Okay. And so keep that in mind. That's unusual. There's actually also, and it's kind of connected to the fact that you start with a radical cation, you end up with a radical cation. There's something that you notice about the nature of the thing that got lost compared to what was getting lost before. Okay, so usually it involved carbon. So that's actually a third thing, man. It usually involves carbon. And it was usually a radical that got lost. And as a result, the fragment that got lost always had an odd number, an odd nominal mass. This is an even mass. And it's a mass of water, right? But in particular, it's an even mass. So if you see the loss of an even mass, you can deduce that it's not the typical radical cation to a radical cation to a cation and a radical. It's something else that's going on. So do take note that this is an even number. So that already makes it different. Okay. And we went from a radical cation to a radical cation. All right. So, when you see this, then it's actually kind of a telltale sign that likely, yeah, it had an alcohol functional group. So keep that in mind. We'll work with this a little bit, if not today, next class. The next one that I'd like you to know about. And so I'll show you these, and then hopefully we'll have time for a little bit of practice. Fragmentation of ketones and aldehydes. And then if you would kindly add in brackets here, this is also seen with esters, with amides, with carboxylic acids, maybe not to the same degree, but it's also seen with these guys. So really, it's the fact that you've got the carbonyl group. Okay, so I'm just going to put underneath here carbonyl. This one has the lovely name of the McLafferty rearrangement. Do you need to know the McLafferty rearrangement? Yes. Also note, we go from a radical cation to a radical cation. Also note what gets lost is an even number. So again, this distinguishes it from the idea of it fragments and you end up with a cation and a radical. Now, I would like you to be able to take a ketone or an aldehyde or one of these other functional groups and predict what the product would be from a McLafferty rearrangement. And so there's a strategy that I would encourage you to take. Now, unfortunately, my labeling here is going to be different than the labeling I used a minute ago. Alpha, beta, gamma. when I was talking about the alpha cleavage, I was labeling the carbon that was right next to the hetero atom as the alpha carbon. And that's definitely true if you're dealing with an alcohol. But unfortunately, when you're dealing with a carbonyl, in most contexts, the alpha carbon is actually considered to be the adjacent carbon. I'm sorry about that inconsistency. So if you can remember in this context, alpha, beta, gamma, as I have labeled them. And to go from the original radical cation to the products, there's a sequence, and unfortunately, this will be paired or double arrows, in other words, pairs of electrons. And when you're learning this, I would encourage you to sort of always start in the same way so that you get into the habit of doing it correctly. So I would start with the pi bond between the carbon and the oxygen. And know that ultimately I'm going to be forming some kind of alcohol group. So I need that pi bond to pick up the proton. And of course, once that pi bond has made a bond with the proton, a proton can only make one bond. So this bond needs to be broken. Bond between the carbon and the hydrogen on the gamma carbon. And in turn, the bond between the beta and the alpha will get broken. So it's a sequence of, since three things happening. In terms of our product, that's the alpha carbon right here. And so that carbon right on the end, right next to the carbon that has the alcohol. And these guys are the beta, pardon me, the gamma and the beta. And so by keeping that labeling, then you can keep track of the various things. If we were to calculate the mass of this fragment, so CH3, CH2, CH2, so that would be 48 for the carbons. I've got 5, 6, 8 hydrogens. And so I add those all together and I got a mass of 56 atomic mass units. So it makes sense that we're going to lose an even number. We're not losing a radical. So again, if you happen to see an even number fragment loss and you suspect you have a ketone or an aldehyde, this is a justification for that. So to finish off today, I'm not sure we're going to have time for you to do a practice of the McLafferty rearrangement. We may need to do that next Wednesday before we go on to infrared spectroscopy. But I want to show you this chart, first of all, just found at the top of page, or pardon me, in the middle of page 52. And note that the first 4 rows are those things that we spent a lot of time talking about. That if you see these peaks, minus 15, minus 29, minus 43, minus 57, well, of course, you're losing those radicals. But if you see a minus 18, note an even number, well, you're likely losing water from an alcohol. If you see M minus X, where X is some other even number, a McLafferty rearrangement is very likely. So you may want to highlight that chart. It is actually quite a helpful reminder. But to end today, let's look at these 2 last check your understanding questions. So this is 9 and 10, 9, 15. Yeah, I think that might bring us to the end. So all of these isomers have a formula of C6H12O. And I'm asking which one would you expect to see an M minus 18 peak? Before I open up the question, I ask you, look at that formula again, please. So if I can get your eyes for a second. So look at that formula, C6H12O. So if it was a typical alkane, what would the formula be? For 6 carbons, C6H14, right? And having an oxygen doesn't interfere with the number of hydrogens. So this is C6H12. So that reminds you that you either have a double bond somewhere in the structure or you have a ring. Right? So every time you lose two hydrogens from the typical alkane, double bond or a ring. So I'm just trying to get your brain to get used to looking at that because you're going to need to look at that a lot. All right, so let's open up the poll. And this is an obvious question. That's great. But try to put yourself in the context of maybe 5 days from now. Are you going to remember this detail kind of thing? So which one are these isomers? So you know you have a compound of the molecular form of C6H12O. And you think, well, is it a ketone? Is it an aldehyde? Is there an alcohol? Well, you might look for the M-18 peak. And I kind of gave it away there. But most of you were already looking that way. So in the interest of time, I will indicate that most of you are saying, well, it's likely choice C then. Because there is a hydrogen next door, so a water molecule could be lost. All these other ones don't have the alcohol group. M-18. Oh, look what I just did. Sorry, my slide went forward. I didn't mean that. I'm still on this question. I don't know about you guys. I'm still on this question, right? Okay, sorry about that. Yeah, okay. Sorry if I confused folks at home as well. No, I'm on this M-18 question, and indeed, the majority, all of you have voted in on that, so that's great. Okay, one last question then. So which of these would more likely undergo the McLafferty rearrangement? And this is question number 10. And I think actually the first question was maybe a little too easy because, yeah, M-18, we're looking for the one that has the alcohol. But this one is maybe a little more tricky. Saying which one can undergo a McLafferty rearrangement? And I said, well, that's good for aldehydes, ketones, possibly esters, carboxylic acids, amides. So I see that the two favorite answers are A and B, which is natural because we've got ketone groups. But actually, the correct answer here is there's only one of them, not both. And so recall that in order to have a McLafferty rearrangement, what has to happen here is you need alpha, beta, gamma carbons, and it involves the hydrogen on the gamma. So now let's come back to where we just were, which is here. So I'm going to do some labeling. Alpha, beta, gamma. And unfortunately, in this context, in spite of what we said about alpha cleavage, in this context, we label it like this, right? Alpha, beta, gamma. And then here, well, we can go alpha, beta. We can go alpha, beta. We can go alpha, beta, but there's no gamma. There's no carbon that's out enough with a hydrogen that would allow for just the right positioning for the McLafferty rearrangement. Wow, everyone has chosen the correct answer. Pretty amazing. And indeed, the correct answer is A. And I do want you to have some practice with the McLafferty rearrangement. So at the beginning of next class, we'll do that. We'll do a little mystery determination, and then we'll start to look at infrared spectroscopy. I hope you have a safe weekend, that you're able to reflect on the importance of reconciliation, and that you're well. So thank you as always for your kind attention.